All right, let's look at example 326. Use Gauss-Jordan to solve these three equations. Now notice, if we think about this geometrically, these are three planes. And when you have three planes, you can either have no solution, a single solution, or infinitely many solutions. Just looking at this one right off, I can tell no two of those planes are parallel to each other. But that doesn't really tell me anything about how many solutions they have. They might all meet in a line. They might do this number where they don't have any common points, or they might have a unique solution. So let's use reduced row echelon form to solve it. So first up, I'm going to write it as a matrix. Let's see, 7, 0, 6, 1, 12. And I'm going to use this 1 here as a pivot to clean out the first column. So I'm going to do row 2 minus 3 row 1, and row 3 minus 7 row 1. All right, when I do that, row 1 stays the same. Row 2 minus 3 row 1. So we get 3 minus 3. Then we get negative 4 minus 3. Then we get 2 minus 3. And then we get 28 minus 63. It's negative 35. Then on the bottom, let's see, we get 7 minus 7. Then we get 0 minus 7. Then we get 6 minus 7. Interesting. And then we get 112 minus 7 times 21. It's negative 35. Now, as soon as we get something like this happening where two rows are exactly the same, that means that those two rows, basically, they're the same equation. So it's going to lead us to a row of all zeros, because I'm going to do row 3 minus row 2. So that shouldn't be a 0 there. That should be a negative 35. So we've reduced this to a system with two planes. And we can look at that and tell two planes that are not parallel. We know they're not parallel because this is not a multiple of that. So the original system has the same solution set as these two planes. And if those two planes are not parallel, that means they're intersecting somewhere. So we're going to get a whole line of solutions in three-dimensional space here for this thing. So what I need to do now is get a pivot here. I'm going to get a 1 there, and then I'm going to use that to zero this out. So I have to do row 2 times, or I'll do divided by negative 7. Now that's not going to be too bad. It's going to give me one fraction. It's going to give me 0, 1, 1/7, and 5. And now I'll use this as my pivot, and I'll do row 1 minus row 2. So I get 1 minus 1, or I'm sorry, 1 minus 0, 1 minus 1, 1 minus the 7th, and then 21 minus 5. And we're almost done. We've got to write this back as a system because we want to write the solution out, and we're going to do that in parametric form. So let's we know this is x, y, and z. So notice x and y both have leading ones, but z is going to be a free variable. So I can write this solution as x equals 16 minus 6/7 z. Notice what I'm doing here. This top equation says x plus 6/7 z equals 16. I'm just going ahead and moving this to the other side and making it negative. The second line gives me y equals 5 minus 1/7 z. And then z is free, so it's just z equals z. So this is my parametric solution. If you want to, you can go back in and replace the z with a t. That's what our book is going to do. We're going to go back in. It's fine with me if you just left it as z, but the book is going to change that to t. And so that's the solution for this. And that right there would give us that plane in three-dimensional space. I'm sorry, not a plane in three-dimensional space, a line. Let's graph that and see what it looks like. I'm going to go back to my plane graphing tool. Let's see. The original plane that we looked at was, or the original three planes were 1, 1, 1, 21. Then 3, negative 4, 2, 28. Then 7, 0, 6, 112. So let's see if we can see. Yeah, we can see it right here. If you look at this, is that on the screen good? Yeah. Well, unfortunately, I can't zoom to it very well. But you can look at it and see these are three planes, and they all three intersect in a line. And you can get all the points along that line where they intersect by picking a value for t and plugging into that parametric solution. All right.